In today's lecture, we will talk about the inverse Z transform, and this topic will be divided into two parts, and this is the first part of the lecture. In this first part, we will talk about the inverse Z transform, which is mainly given the Z transform of a signal, we need to find what the signal is. And then we will talk about partial fraction expansion, which is a useful tool in finding the inverse Z transform, and we will work on an example to apply the partial fraction expansion to find the inverse Z transform. The inverse Z transform is basically the following problem. Giving the Z transform of a signal, which is x of z, with the corresponding ROC, the problem is to try to find what is the actual signal x of n, which is the signal in the time domain. Now, for that, to do this, there is a general formula which involves a contour integral, which is the following here, that gives you at each time n the value of the signal as an integral involving the Z transform of the signal. Now, the formula looks a little bit complicated, but there is some good news, is that we won't be using this formula here because we were going to use a more, I would say, an easier way of finding the Z transform that doesn't involve a contour integral here. But I just want to include this formula to tell, in order to tell you that there is a general formula to find it. So in this course, mainly we were going to be dealing with finding the inverse Z transform of rational functions, which we talked about in the previous lecture. So a rational function is a function that is the ratio of two polynomials. So it can be written as this form. So you have a polynomial as a numerator and a polynomial as a denominator. And for these types of Z transforms, there is an easier way of finding their inverse, which does not involve the complicated formula that I just mentioned in the previous slide. And the way we're going to find the Z inverse here is to divide this rational function into sum of parts, where we can identify each part, the inverse of each. And I will try to clarify this idea in the coming slide by working out a few examples. So let's jump right into it and try to solve the following example. The example here consists of finding the inverse Z transform of the following Z transform. And you can easily see here that this Z transform is a rational function because it's a fraction with polynomials in the numerator and in the denominator. Now, if you remember the example we saw early on, maybe in the first lecture of this course, which was concerning the Z transform of an exponential signal, a right-sided exponential signal. So we know if we have the following signal, let's call it x of n. So x of n, it was a n u n. We know that x of z is z divided by z minus a, and the region of conversion is z greater than a. Or if we multiply by z minus 1, we get 1 divided by 1 minus a z minus 1. Now, what does that mean? This means that if you could answer the following question. So if I tell you what is the inverse transform of x of z equal to 1 minus 1, let's say half z minus 1. If and z greater than 1/2. So if you see this, you can immediately tell me that x of n here is equal to, so you know that a here is 1/2, so it's 1 over 2n u of n. So you don't need a formula, you don't need to apply the contour integral in the previous that I showed on the first slide, and I didn't really go into it. And so this is what basically the main idea we want to apply. we want to divide a rational function into sum of parts where each part we know the inverse of. And this is what I want to do for this complicated function. So if you look at this function here, it's a rational function like I mentioned, but it's not, it doesn't look like something I've seen before. So for this reason, what I'm gonna do, I'm gonna divide it into to look like something that I've seen before. So I'm gonna divide it to be the sum of terms that look like this term here that I've worked out before. So I want to divide it into a sum of terms where the numerator and the denominator have degree at most 1. And here, since here the degree is in z minus 1 is 2, so I need 2 parts or 2 terms in the sum in which each term has, the denominator in each term has degree 1 in z minus 1. So I'm going to try to divide it into these terms, into this sum. And you can see that this sum here, if you try to find the common denominator, it's going to give you a denominator with degree 2 in z minus 1, which is exactly what we have here, and possibly degree 1 in the numerator, which is what we have here. So this is kind of, this is the correct form, because again, if you try to find the common denominator, you're going to get something like this: 1 minus ez minus 1 times 1 minus z minus 1, and you're going to get something like this. I'm all switching the pen, so let me fix the pen. So it's a times 1 minus bz minus 1 plus b 1 minus az minus 1. So the reason I'm doing this is to tell you that it makes sense to see that this thing here can be written as this form, because you can look here that maybe the term in z minus 1 will cancel each other, or maybe not. So, but the degrees match. So I have a denominator with degree 2 in z minus 1, and that's what I have here. And here I will have a numerator with degree at most 1 in z minus 1. So it makes sense. So the whole question here is to find a and b. So that's, if I can do this, then I would have solved the problem. Because once I find a and b, then I can apply this formula here, and I have the inverse z transform of each one separately. Okay, and we call this partial fraction expansion. So this is partial fraction expansion. Again, the idea is to divide a complicated rational function into parts where the numerator and the denominator have degree at most 1, so I can invert them separately based on the easy formulas that I know. So our goal to write this function here in the following form by doing partial fraction expansion. So I'm going to write it here. So it's going to be equal to some constant capital A divided by 1 minus small a z minus 1 plus some constant capital B divided by 1 minus b z minus 1. And like I said, maybe I forgot to mention in the previous slide here, the question is find the constant capital A, the constant capital B, but also, I guess I forgot to mention this in the previous slide, find the poles small a and small b. And to do this, all I need to find is solve this is equal to 0. Then I find the poles, and here the poles, I will get 2 poles. One pole that is, I can see that one pole is 1/2, and one pole is 1/4. So if you solve this as a function, it's just a quadratic equation in z minus 1. So if you find the delta, the discriminant, and you just solve for it, you get 2 solutions, 1/2 and 1/4. And then you write this function as a function of the poles. So that's the first step. So let me highlight this here. So the first step is to put it under this form, meaning to factorize the denominator and the numerator. And why do I need to do this? Because once I find this form, I know the small a, the value of small a and small b. So now I know that here, this is equal to actually capital A divided by 1 minus 1/2 z minus 1, because this is 1/2 here, plus capital B 1 minus 1/4 z minus 1, because 1/4 is here. So the next step would be to find the constant capital A and capital B. So again, first step is find the zeros and the poles of x of z. So after finding the poles and the zeros of x of z, I can write it under this form here. And the question now is, how can I find capital A and capital B? And there is a trick here to do it. And you probably know it. In case you don't know it, I'm going to remind you of it. The trick is to first, you cancel out the denominator of A, if you want to find A. So to cancel out the denominator of A, I have to multiply by the denominator. So I multiply everything by 1 minus 1/2 z minus 1. So I multiply both, the whole equation, by 1 minus 1/2 z minus 1 on both sides. So what do I get? So here this thing cancels out here, so I would get 2 times 1 minus 1/3 z minus 1 by 1 minus 1/4 z minus 1 here, equal to A. So A is now singled out, plus B times 1 minus 1/2 z minus 1 divided by 1 minus 1/4 z minus 1. Okay. Now, how can I cancel out B? If I want to cancel out B, I can take this term to be equal to 0, which means that I can set z minus 1 to be equal to 1/2. I'm sorry, to z equal to 1/2, or z minus 1 equal to 2, right? Because this means that 1/2 z minus 1 equal to 1, z minus 1 equal to 2, or z equal to 1/2. So I plug in z equal to 1/2 in the whole equation. You're going to zero out b, and you're going to find the value of a. So a equal to 2 times 1 minus 1/3. Here z minus 1 equal to 2. 1 minus 1/4 times 2. And this will give you the value of a. And to find b, I'll do the same thing. So this slide explains maybe in a cleaner way how I can find a, like I mentioned. So I have to multiply both sides by the denominator of a. And I do this to kind of single out a. And then I zero out everything that multiplies b by taking this term to be 0. And I get, and taking this term to be 0, meaning taking z minus 1 equal to 2. And this will give you exactly what I had on the previous slide, which gives you a equal to 4/3. So we just found the first value that we needed. So we just found a. Now, to find the value of b, I multiply both sides of the equation by the denominator of b. And the denominator of b here, I'm going to highlight it in yellow, is this one. So this way I have b singled out here. And to get rid of a, what I do is I set this term equal to 0. So I set this term here equal to 0. This means I set z equal to 1/4, or z minus 1 equal to 4. And this way you get b equal to 2. 1 minus 1/3 times 4, which is 1 minus 4/3, divided by 1 minus 1/2 by 4. So you get b equal to 2/3. Right? And this way we solve the problem. So we have our constants capital A, capital B, and the poles A and B, and then I can write the kind of what we started with, the rational function, the complicated rational function, in terms of sum of terms of smaller degree, which I know how to invert. So now I can write x of z as 4/3 divided by 1 minus 1/2 z minus 1 plus 2/3, which is the b that I just found, divided by 1 minus 1/4 z minus 1. And you can see now, hopefully, that it's easy to invert each of these terms. Now, the thing to take care of here is that the ROC was not clarified in the question for the reason because I want you to study the different cases, and that's what I want to do next. So I want to analyze the inverse of each term separately. So we know for the first term here, this one, that the inverse is a right-sided signal for capital Z, or for the magnitude of Z greater than 1/2, or it's a left-sided signal for the magnitude of Z less than 1/2, right? Because the pole is 1/2. And for instance, when for the right-sided signal, then the inverse here would be, like I just mentioned, would be 1/2 to the power n un, right? And similar thing for this term here. So it's going to be a right-sided signal for when the magnitude of Z is bigger than 1/4, or a left-sided signal when the capital of Z, or the magnitude of Z is less than 1/4. So we have these four cases that we need to take care of. The first case is whether, let me draw the Z-plane, the pole zero plot. So I have 1/2 here, or 1/4 here, and 1/2 here. And I mean, you're going to have the cases where either Z is greater than 1/2, right? Or Z is smaller than 1/2, or Z bigger than 1/4, or Z smaller than 1/4, maybe. So we need to analyze. It seems that there are four cases here, and that's what we need to analyze. And for each case, we need to find the inverse signal. So in this step, we analyze the ROC of each term, and we combine them together. So the first, and we have, like I said, in principle, all combination, you have four cases. The magnitude of Z is larger than 1/2, and the magnitude of Z is larger than 1/4. So this corresponds to the case where magnitude of Z is greater than 1/2, or magnitude of Z is greater than 1/2, and magnitude of Z is less than 1/4. And actually, this case is empty, so it never happens, and so on and so forth. So in fact, we have, in the end, three cases. So I'm going to try to draw each case. So in this case here, I have the two poles, 1/4 and 1/2. And this case corresponds to the amplitude of Z is bigger than 1/2. And this case here corresponds to the inner ring between 1/4 and 1/2. And here is, so 1/4 and 1/2 is the inner part of the inner circle. So I hope you can already see that this is basically the right-sided signal, and this is the double-sided, and this is the left-sided signal. And now in the last step, what we can do for each of these cases, we invert, or we find the inverse Z transform. So let me remind you of what was my the fractional the fractional expansion of our function. It was, so x of z was equal to 4/3 1 minus 1/2 z minus 1 plus 2/3 1 minus 1/4 z minus 1. And again, the important thing to know here, and I'm going to write it maybe in red, is that to know these two results, I'm going to write them maybe at the bottom of the slide. So if you have 1 over 1 minus a z minus 1, then the inverse of this, if the signal is right-sided, meaning z is greater than a, then the inverse is x of n is equal to a of n u of n. And if the signal is left-sided, so left-sided signal meaning z is less than a, then x of n is equal to minus an un minus 1. So we did these two examples in the very first lecture. And what I do here, I just apply these formulas. So I know that in the first case, if you remember, in the first case, it was the case when both signals were right-sided. So that's why I have, so here the 4/3 is going to be 4/3 here, and the inverse of this term here, so this term here is going to be 1/2 to the power n u of n, and this guy is 2/3, 1/4 to the power n u n. So both signals are right-sided. In the fourth case, both signals are left-sided, and this is why I'm applying this formula here. So I have 4/3, 1 over, we have the negative sign, 4/3, 1/2 to the power n u minus n minus 1. So you can see here that the signal is left-sided, and the second signal here is left-sided. And the one in the middle, the third case here is the first signal is left-sided, and the second signal is right-sided. And the second case does not exist. I don't know, here I wrote no convergence, but actually should be is an empty case. So it's, this case does not exist actually. So it's an empty case, meaning there is no z that satisfies these conditions. So in the end, this is the answer to the problem. So for that z transform, if I don't specify the ROC, then there are multiple cases, and these are the cases that exist. There are three cases, whether the whole signal is double-sided or left-sided or right-sided. So here I just noticed that I had a typo. When the signal is left-sided, then the inverse is negative a to the power n u minus n minus 1. So here I left out the negative sign here, so I'm going to add it. So here there is a minus signal. So maybe if I try to erase it, yeah, so I guess so that's what's going to be. There's a negative signal here, and this is why you have these things here. So I want to end with a problem that I hope you can do it at home by yourself, which is the following. Find the inverse z transform of the following function. And here, to make it easy for you, I'm specifying that this signal is right-sided, so you don't have to do all the cases. So basically, the main issue here is to just do the partial fraction expansion and then see what you get. And again, feel free to post your response to Piazza and check it with your friends.